In an industry that builds nations, information is power. Insight is strategy. The steel and mining industry drives the backbone of modern infrastructure. But in a rapidly changing market, every decision needs reliable intelligence. It began with a simple idea: a morning WhatsApp news update for the steel and mining industry. The updates quickly gained industry participation and credibility across the sector. This growing community led to the formation of Metalogic Research and Advisory. During the global disruption of COVID, we launched our digital intelligence platform, mymetalogic.com. A central hub delivering market intelligence, industry analysis, and strategic insights. From daily market movements to weekly strategic analysis, our reports keep the industry informed. Our consultancy services support businesses with market research, commodity pricing, and industry analysis. Through myMetalogic memberships, industry professionals gain exclusive access to market intelligence and premium reports. myMetalogic, intelligence powering the future of the steel and mining industry. India's steel and mining industry is evolving faster than ever. But real progress happens when ideas, technology, and leadership come together. With 10+ years of experience, Metalogic has been connecting the steel ecosystem through impactful industry platforms across Pan-India. We bring together CXOs, plant heads, innovators, and decision-makers shaping the future of steel and mining. Focused events for the steel and mining sector. Tailored, customized events designed for your business goals. Research-driven forums delivering real industry insights. Powerful product and company launches that capture attention. Because we don't just host events, we create industry brands. From brainstorming sessions to live demonstrations, we create spaces where innovation comes alive, and exhibitions that showcase the technologies shaping tomorrow. Metalogic events, connecting ideas, industry, and innovation. Join us to shape the future of steel and mining. In an industry that builds nations, information is power, insight is strategy. The steel and mining industry drives the backbone of modern infrastructure. But in a rapidly changing market, every decision needs reliable intelligence. It began with a simple idea: a morning WhatsApp news update for the steel and mining industry. The updates quickly gained industry participation and credibility across the sector. This growing community led to the formation of Metalogic Research and Advisory. During the global disruption of COVID, we launched our digital intelligence platform, mymetalogic.com. A central hub delivering market intelligence, industry analysis, and strategic insights. From daily market movements to weekly strategic analysis, our reports keep the industry informed. Our consultancy services support businesses with market research, commodity pricing, and industry analysis. Through MyMetalogic memberships, industry professionals gain exclusive access to market intelligence and premium reports. MyMetalogic
We're ready to start. So, good afternoon, everyone. A very warm welcome to all our distinguished speakers, industry experts, and participants joining us from across India and around the world. I'm Monica Bachchan, founder and CEO of Metallurgy Projects Management Services, and it is my pleasure to welcome you to Metallurgic's 67th webinar on advanced iron ore agglomeration through sintering, presented by Abhitech Energycon Limited. Thank you all for taking the time for us today. Before we begin, let me quickly share a few housekeeping announcements. This webinar is being streamed live on Metalogic YouTube channel. So if you know your colleagues or industry friends who would benefit from today's webinar, please go to the youtube.com on your application, type Metalogic PMS, and you will find the live of this webinar. We encourage everyone to actively participate throughout the session. Please feel free to post your questions in the question and answer box, and we will take it up as many as possible during the Q&A session. And here's something exciting. We have a live quiz at the end of today's webinar. So stay attentive, take notes, and listen carefully to our expert speakers. It is a great opportunity to test your knowledge and make today's session even more interactive. Now, coming to today's topic. Iron ore sintering is one of those processes that sits quietly at the heart of integrated steel making, but its impact is anything but quiet. The quality and consistency of sinter directly influence blast furnace productivity, fuel consumption, raw material efficiency, and increasingly the carbon footprint of steel making. And today, sinter plants are operating in a much more challenging environment. We are dealing with changing ore characteristics, increasing gang levels, pressure on productivity, quality requirements, and at the same time, the need to reduce energy consumption and carbon emission. So today's discussion is not simply about how to make sinter. It is about how to make better sinter consistently and efficiently under changing raw materials and operating conditions. We will look at the challenges right from raw material optimization to blend designs to sinter quality, productivity, technological interventions, and industrial case studies, the impact of sinter quality on blast furnace performance, and finally, the critical question of decarbonizing the sintering process. And we have an excellent panel representing technology, R&D, and operating expertise from across the sinter industry. Allow me to introduce our esteemed panelists to you all. We are today joined by Dr. Rameshwar Shah, Senior Vice President R&D Metallurgy, Abhitech Energycon Ltd. Mr. A.V. Bushan, Director Steel and Innovation, Abhitech Energycon Ltd. Mr. AVB Acharyulu, GM R&D, JSW Steel. Mr. Rakesh Ambastha, Chief of Agglomeration, Tata Steel Kalinganagar, Tata Steel, and Mr. Anish Mohapatra, Section Head, Technical Control Group, Sinter Plant at ArcelorMittal Nippon Steel India. And I'm your host, Monica Bachchan. Ladies and gentlemen, please allow me to join me in extending a warm welcome to all our esteemed speakers. So, without further delay, let's begin our discussion. To set the context, may I now invite Dr. Rameshwar Shah, Senior Vice President, and Mr. A.V. Bushan, Director, Steel and Innovation from Abhitech Energycon Limited. Over to you, Dr. Rameshwar and Mr. Bushan.
Thank you, Ms. Monica. Thank you very much for that good introduction and start for the webinar. Thank you once again, all of you, and thank you for taking your time off for this webinar. And what we shall do now is present to you a simple presentation that we have put together. And this will talk about the sintering process, its challenges, and some of the technology interventions that are possible today to improve the overall process of sintering and make a significant impact to the overall hot metal production and the profitability consequently of the steel plant. So with that, I will request my colleague, Dr. Rameshwar Shah, to start the presentation, please.
Good afternoon, all. I welcome all the participants, all the audiences, and thanks a lot for giving us the opportunity to share our know-how technology on the advanced iron ore agglomeration through sintering. The topic of the webinar is very apt and relevant to the steel industry because anywhere for any integrated steel plant, it is the sinter making which is the heart of the iron production, and that in turns are making the steel. So moving on to the slides, I have divided my presentation into 5 subtopics, which basically goes through the journey, right? How basically the sinter contributes to the steel making. So once we talk about the sinter, how can you forget about the steel? So looking at the global and Indian scenario of the steel making and their growth by 2050, what you find that the global steel production is going to increase its current level of 1,985 million ton to the level of 2,500 million ton in the next 25 years. So overall, we see that this industry is going to grow globally at a CAGR of 1% only. While in India, the steel production capacity that has been charted out by the Steel Mission in 2030 and subsequently to the Viksit Bharat, that is 2047, it is to the level of 500 million tons of steel productions. So India is growing with the steel production at a CAGR of closely around 4%. The share of the Indian steel will rise from 9% to the 20% by 2050. Now moving on to the details, how actually this and why the sinter is important to that. If you look at the vital statistics of the steel by the year 2025, we see that India has an installed steel making capacity of 220 million ton. The crude steel that we have produced in 2025, 168.4 million ton, and the finished steel goes to 161 million ton. What we find that the almost 46% of the steel that India is producing is coming through the blast furnace and BOF route, and where the hot metal that India produced is close to 95 million ton. To produce the hot metal that is for the steel making, the sinter is the prime feed materials, and India is currently producing to very close to the 100 million tons of sinter every year. And the rest of the requirement that is for the steel making are there, which in terms of the coal and coke fluctuation and others. What basically we see, just to begin with fundamentals of the sintering, because there may be the audiences who are from the, you can say, the research background, maybe the steel maker, the sinter plant operators, experts. But we must know what the sinter is. It is basically a thermally agglomerated product of iron ore fines, the fluxes, many other fines, and a lot of waste that is recycled for making the sinters. And it is a strong, porous, and lumpy mass, which is the most suitable, you can say, iron bearing charge feed for the blast furnaces. What we see, basically, look at the processes that we'll discuss in detail later. The whole sintering, basically, the two things are more important in the sinter making. That is the granulation and the bonding phase during its sintering. It is basically the incipient fusion of the material which makes this whole heterogeneous mass very much homogeneous, and that the product that we produce, it is highly, you can say, homogeneous and consistent in quality, which is the feed to the blast furnace. Now, basically, what to say, before we going for the key challenges, let me tell what actually the process. This we are not going in detail about the iron making processes, but what we see that in iron making, basically, we all the iron bearing materials to the coal, coal and fluxes. Finally, when it goes to the furnaces, how it impacts the behavior of the furnaces. So what actually we need by or mean by the good sinter? A good sinter is one which is having a strong room temperature, high temperature properties, very good result, you can say, reducibility, which is the right feed to the blast furnaces. And then this strong sinter, this good quality sinter, will lead to basically a very good production, very good, you can say, kind of the hot metal and all the properties of that. For that, the sinter properties that we need, which must have, you can say, their properties in the range what we have mentioned. So the good quality sinter must possess, you can say, a higher tumbler index, the RDA properties and reducibility. What actually the operating parameters that we basically the sinter makers need, what could be the FUO content, what could be the, you can say, their for fuel concern, what kind of porosity could be there, so that make it a right kind of the product. Now, basically, moving on to the slides, why actually sintering is done. Sintering is nothing new, a kind of the product, and the sinter industry, it is a very established process, more than 100 years of age-old process, and it has got time and again a fresh lease of the life. So basically, the sintering, where if you look at the mining of the iron ore, because of the mechanized mining, and you can say we generate almost 65 to 70% of the fines. By fines of the iron ore means it is less than 10 millimeters. So these kind of materials cannot be directly charged into the blast furnaces. So this almost 2/3 of the material which is produced in the mining, how best we can utilize, and for that the agglomeration is required. Sintering is probably the most economic and widely used agglomeration process. It is a mass which is basically heterogeneous as the input, but once you make a product, it is highly homogeneous. And this is very consistent kind of the product, and which having its embedded properties, which are very good, you can say, porosity, very good strength, that becomes basically in the blast furnace, that is there the main feed. It is basically the lifeline of the, you can say, the charging material for the blast furnaces. What we see basically, the major feed that blast furnace all over, you can say, either India or abroad, sinter basically accounts for almost 50 to 70% of the iron ore charge mixed in the furnaces. And that's why this whole functioning of the blast furnace becomes very smooth if we have a very good quality of the sinters. So there is going to be an increasing demand of the blast furnace, increasing demand of the sinters, because more and more number of, because of the capacity expansion of the steel in India, more and more number of blast furnaces are coming. So most of the expansion are through the BF and BF route, and that basically requires, or there is going to be a good demand or very high demand of the sinters. Now there could be, we come to the challenges. Now the challenges, there are plethora of challenges. It is not only for the sinter makers, for the whole steel industry. There is going to be the first 5 that you can say the challenges that you mentioned. It is all related to the raw materials. So as we have gone over the years for the preferential and selective mining of the iron ore, now basically we have almost exhausted the high grade ores. So it is only the low grade. The low grade refers to less of the iron component into the iron ore and more of the gangue materials. So those are the impurities, and that we need to handle. And to handle those materials or the microfines that we generate, that makes the sinter making very, very, you can say, challenging. Beyond that, if you go for the sinter makers, it is the more important part is there the operating parameters, how basically the critical processing parameters they maintain. And once they produce a sinter, there is the process is designed in such a way whatever this lumpy mass needs, we need to again, you can say, size it, make it a suitable size range, which is you can say amenable for the blast furnace as a feed. So during the sizing and this crushing processes, we generate a lot of fines. Every steel plants or those who are operating the sinter plants, they generate invariably 30 to 40%. That is the range their sinter return fines, which is less than 5 millimeters. This is all either through recirculated. It is something which is basically making our process more reliable. And to overcome all this, we need a lot of, you can say, the predictive models, the new systems, the new, you can say, know-how, the new technology, all those for, you can say, making good quality sinter. At the same time, this processes is sintering. It is highly dust and other emission additives. So we need to be very compliant to the environment norms too. Now moving on basically to the raw material parts. Here basically we see these are you can say the different kinds of the challenges which comes, but challenges to the sinter is basically challenges of the iron ore itself, because that is the main raw material part. And there all this increasing the gangue minerals, which basically makes your whole process very, you can say, stringent and more, you can say, costly. If the more gangue materials are there, you need more fuel requirement. You are making the more of the slag and less of the metals. So all these higher silica, alumina, alkalis, or all these fines, they are all your basically the process system of blocks. So how to handle that? That basically makes the challenge for making the raw material parts of this sinter. So moving on, this very precisely what the silica. This is silica. These are all, you can say, undesirable things. But it is not absolutely, you can say, undesirable. Certain amount of silica is required because it helps in making the slag phase, which is for the good for the bondings. Because if the slag phase formation will not be there, we will not be able to produce a good quality of the sinter, a stronger sinter. So looking at, you can say, the trend, what we see, beyond 4%, if the silica is there, it is going to be more, you can say, poor in the quality of the sinter products. It all reduces their strength, properties, as well as the reducibility. Similar is probably the effect of the alumina. Alumina, rather, I would say it is a bigger problem than the silica for the sinter makers. Because this alumina being a refractory mass, it is having higher melting point. It basically reduces the melt viscosity. It, you can say, reduces or it stumble blocks for making the SFCF formation, which is the strong bonding phase. It makes your bonding poor, and ultimately you are landing up with a very poor quality of the sinter. So this alumina that basically needs to be handled, and there are ways how basically invariably earlier we say combinedly the silica and alumina should not be more than 5%. But the time has gone. Now the materials that are available, we have to live with that. In India is having so much of reserves of the iron ore and coal that we have to make the whole, you can say, study self-reliant and, you can say, sustainable. Coming to the microfines, that there are two terminology in the industry normally used, which is less than 0.5 millimeters also for the microfines. People also sometimes use less than 0.15 millimeter, that is 115 micron. All these fines are basically, you can say, detrimental for the sinter making processes. What these fines does during the processes of the sinter making, it basically fills it doesn't help basically to granulate the sinter, you can say, green mass. So what actually does, it either fills up the pores and thereby it blocks the flow of the gases. Once the flow of the gases becomes, the process of the sintering becomes very slow because your permeability goes down. So all these microfines, there has to be limitation. And looking at the graph, what we can see, if it is to the level of 25 to 30% in that, because some microfines are required, because coarser fines in the granulation acts as a nuclei and the finer particles get coated, and that is the basic principle behind the granulation of the sinter mass. But if it goes beyond the 30% or so, it basically is harmful for making the good granules and ultimately making the permeability and others. Now basically going to the another, you can say, that is for the sinter, it is a lime quality. So normally people we need to maintain certain basicity in the pellets, and for which people add the flux. That is mostly invariably everywhere they use either the limestone and the dolomites. What the advantage of the burnt lime is there, it has very extremely high reactivity, At the same time, it has a very larger surface area. So this basically helps in the binding, improving the granulation also. At the same time, since this is a calcined mass, it doesn't need heat there into the sinter making furnaces. Rather, it transfers the more faster the heat to the iron ore particles, making this incipiently fused faster and making it a good, you can say, assimilation. And once this molten mass is getting good assimilated, it basically helps in the whole expediting the process. There the sinter makers takes the liberty of the percentage of, you can say, higher percentage of burnt lime and the quality of the burnt lime to make the process faster or making a better product. Even they can play with the machine, sinter machine speed. If they have the good quality of that better permeability, they can increase the speed and improve upon the production. Now coming to the another aspect beyond this material part, it is the more critical, the sintering process parameters. So it may look, there are many, but all these process parameters, they need to be controlled. Otherwise, the sinter plant's efficiency, maybe in terms of their productivity, in terms of the energy, it all gets lost. So what basically we see, the bed permeability that they maintains, the bed height they maintains, the suction air basically, this is all the, and the BTP that we can say monitor. They can say that we set how basically fast, if you achieve the, you can say, burn through temperature, just you can say before your, you can say, last stage of that, it gives you enough time to increase or to make your sinter faster and increase your speed, through which you can improve upon the productivity. So all these parameters are very helpful. Here, one of the parameters, that is the moisture control into the raw mix, that also plays a very, very big role. So what basically this moisture source, if there is low moisture into the sinter mix, it becomes like a dry mass. These mass are basically like loosened particles. It is ultimately going to hinders your process, your suctions, everything, and that you can say makes your void fill. If it is more, you can say, moisture, this granulation size will be oversized. So maybe you can very large and irregular particles forms, which basically also do not help the process to, you can say, move faster. So there is a, you can say, optimum, you can say, moisture control, that is to the level of 6 to 8%. And that basically helps the sinter bed, you can say, permeability much higher than that. So moisture, and to better to control the moisture, now there are equipments where the, you can say, the online moisture testers are there. Now beyond this, you can say the raw material and other parts, or the, you can say, process parameters, we need to have some technology and the systems intervention that basically helps to improve upon your sinter, you can say, quality, productivity, or to control the process in a better way. Like suppose the materials are not good, and whatever the supplier availability there, we have to live with that. Then what we have to think, what are the external agents or additives which can help us in improvising the process and the equipment. So for that, we need something like certain kind of catalytic or functional additives. So basically it basically changes either some way the material characteristics, or maybe their, you can say, surface behavior, and that will help you that. The processes needs to be automated, because it is a lot of dynamic control models are required, because the process is so dynamic in nature. If you are not able to have the control over that, if you do not probably know how the process is going to behave, depending upon the changing variations, either in the raw materials or maybe the process parameters, that you all need to basically make your process more and more automated, so that to have a better control over the process and the properties or quality of the product. So there are smart moisture controls, advanced ignition systems, and all others. This nowadays, the digitalization parts where this AI, ML other helps to make a lot of predictive models, which is basically dynamic control models. And all these basically helps to transform your sintering process to a level higher, where you can say have basically less of the manual intervention and more of the automation in the system. That makes your iron making product very competitive and very cost effective. So the next generation sinter, those require all these properties which we can achieve through these systems and the technology adoptions. Now coming to the certain, you can say, predictive models also. So there are a lot of, you can say, now either the softwares, the different control models are there, which can be developed, and they basically in advance, based on the historical data, they predict the sinter properties. If you look at all these properties, this historical data basically helps where your process is getting deviated. So you can control your deviations. There may be the online permeability monitoring, which basically keeps on giving basically the online the real-time information, how basically you control the variations, how your bed is behaving, how basically it enables you the timely control of your section and speed or master, all the parameters which will help you. There are, you can say, online the sintering, you can say chemistry analysis. This equipment helps you basically how basically control your basicity other parameters, and that in turn helps you to make your product how you can say it is a strong, means it's a strength properties and the final property. So all these predictive you can say models are very much like a guide to the operators where they can control the processes, and by controlling the process they can control their product quality as well as the productivity. So similarly, now coming to that, the Sinter, on an average, you can say steel plants is a very energy intensive, you can say, industry, and it almost, you can say, controls more than, you can say, 12% of the energy that is you can say produced, and it also quite emissive because 8 to 10% of the CO2 emissions coming from the steel industry worldwide. So here the role of the energy or making the process more energy efficient, that comes into picture. So where basically we see that Sinter alone in the whole steel making processes, it consumes around 10% of the energy. And there the role comes, and Sinter being a process which is the open bed process, almost 40% of the heat is lost into the environment. So what basically we do, we need to capture the waste heat recovery as well as whatever the hot gases that goes out, we need to recycle it. So there are different technology suppliers like you say Prime Metals, VI and others which have the systems. Many of the Sinter plants in India, particularly JSW Steel, they all have basically installed those systems and they are getting the benefits. It is just tentatively we have worked out for a plant capacity of around 2.5 million tons of the Sinter, which produces around 10 to 11,000 per day. That we can say found, you can say, through waste heat recovery system where you can utilize it for the steam purpose or maybe some other drying or many other application of those heats. We can have an annual saving of around 2 to 3 crores per year. All the benefits of this further is that if you control this energy, because you can say the fuel, that you are going to you can say reduce the carbon footprint by you can emitting the lower, you can say, CO2 emissions. So far coming to this CO2 emission that is from the industry, which is from the environmental aspects, what we find that all these waste heat recovery system and you can say the waste heat recovery combinedly around 30 kg of CO2 per ton of Sinter is going to reduce. The more sophisticated, you can say, that the technology that is the MEROS for them, that stands for the maximized emission reduction of the Sinter. What we see there basically the fugitive emissions as well as the solid particulates going into the air, which is the airborne particles, it reduces it to the less than the 10 milligram per nanometer, where the you can say if the system is not there, it may emit 60, 70 or so. So it makes your environment quite pollutive and it is not good for health also. Now basically the basic context setting kind of the, you can say, the stuff that we have completed. Now to address some of the challenges that the Sinter plants are facing or Sinter is facing, we have very innovative products, which I now hand over this presentation to my senior colleague, Mr. A.V. Bushan.
Thank you, Dr. Shah, and thank you very much. And very well context you have, background you have laid for the right from importance of sintering to the challenges faced in sintering and the various options available to the plant operators. Now, quickly moving on to the technology intervention. One of the technology interventions that we are talking to you about today and which we would like to introduce to you today is a product called SynCat. This is basically a catalyst. It's a multifunctional catalyst for the sintering process. Now, as most of you already have gone through this process of sintering and you know what the challenges are present, we have addressed some of the challenges and designed the product to meet some of these deficiencies and challenges in the sinter process. So this product improves the nodelization or the Bolling index of the sinter mix. It also significantly reduces the BF return fines, the internal fines as well as the blast furnace return fines, and therefore overall increasing the sinter yield, the net sinter yield. Okay, it also enhances sinter quality by improving the strength properties like TI, RDI and RI. And these in turn lead to efficiency improvements in the blast furnace in terms of coke rate reduction as well as hot metal increase in the hot metal production. Next, please. So I will quickly go through the working principle, the sintering process. The Syncat is basically a product which has been designed to absorb the binder molecules on the surface of iron ore, and it forms a very good bridge in the iron ore particles. It increases the bonding strength, both the adhesive and the cohesive strength, and therefore improves the Bolling index. So when this happens, you have an improvement in the overall sinter quality and reduction in the fines because the strength of the sinter also improves. Next, please. So what we have done is, these are the case studies actually. We have taken trials of the product at the R&D, at our own R&D, and these are some of the results that we have got. We have also done a commercial scale plant trial in one of the plants in India, and we have got very good results, which is displayed on the right side of the screen, the field trial results. So let me go through the R&D lab test results. You can see the reduction in the sinter fines were very significant, 3.22 unit reduction. Okay, and similarly, there was an improvement in the tumbler index, and of course, the improvement in mean size. The increase in the mean size obviously has a huge impact on the performance of the sinter and the blast furnace. Similarly, in the field plant trials, which are at an integrated steel plant in India, we have been able to show an increase in the sinter production along with an improvement in the mean size and a reduction in the blast furnace fines. So if you see the -5 mm or -6.3 mm fines reduction has been very significant, 30 to 40%. So this led in turn to the reduction in the coke rate in the blast furnace by as much as 5 to 6 kg per ton of hot metal, which is very significant factor. Next, please. So there is a typical sensitivity index which is followed by most of the steel plants in how to assess the impact of various products or certain technology interventions on the blast furnace. Because of the variations in the process, and some of these are, the impact may not be able to measure all the time. So there is a sensitivity index. So we have given broadly the 4 important sensitivity indices, so to say. The improvement of the mean size, what are the impact? The impact is 3 kg of coke rate reduction in the blast furnace, which can result in a savings of almost 11 lakhs per day, and along with an increase in the hot metal production of 2%. So if you see improvement in the mean size and then reduction in -5 mm in the skip sinter, which is the final sinter going into the blast furnace, and similarly the increase in tumbler index and improvement in RI. These 4 factors or criteria have been considered here, and then minor or improvements in that or improvements have been considered and monetized. When you take in the total value, which is almost obtained, is close to 70 lakhs a day in Indian rupees, which is about $75,000, $70,000 a day. Okay, this is on a basis for a 5 million ton sinter plant gross sinter production per day. So this, of course, we have considered that all the sinter will be used in the blast furnace, which will result in roughly 11,000 tons of sinter production, hot metal per day. And we have considered a coke price of roughly $330 per ton or 32,000 rupees per ton, and a hot metal conversion cost of 7,000 rupees per ton. Next, please. Similarly, there is another technology intervention that we are working on, and this is to develop a catalyst to reduce the coke grease consumption in the sintering process. As all of you are aware, coke grease is a product which is used to impart the fuel requirement and the carbon requirement, and therefore the temperature also rises, and this is considered a valuable material today. So by improving the combustion reactions kinetics, we are trying to reduce the coke grease consumption in a sintering process. This is the working principle is, if you improve the coke reactivity, it results in a faster carbon to oxygen reaction and a better carbon conversion. Therefore, it results in more effective heat release and lowers the coke requirement. Next, please. So these are some of the technology solutions that we provide for the steel process. We are very prominently present right up to the iron zone, and I will not get into the technical details of each of the product, but right from the beneficiation process to blast furnace, we have got products including sintering, and these add value to the operations and improve the overall process efficiency of various unit operations in the iron process. next. So we would be very happy to discuss with you and provide any suitable solution for your sintering challenges and related issues. Thank you very much.
So thank you so much for this wonderful presentation. I hope I'm audible.
Yes,
And I request Mr. Dr. Rameshwar to stop the sharing of the slide. We will now begin the panel discussion. And viewers, let me inform you that this particular session is brought to you by Abhitech Energycon Limited. A little about Abhitech is it is led by the founder and chairman, Mr. Ganesh Samant, has been working on this technology-driven solution in energy efficiency, process optimization, and industrial decarbonization. The company has also been associated with innovative solutions for the iron and steel industry. And now let's begin the panel discussion. We will start from Mr. Rakesh Ambastha, who is the Chief of Agglomerates, Tata Steel Kalinganagar at Tata Steel. Mr. Rakesh, at Tata Steel Kalinganagar, how do you manage variability in iron ore fines and other raw materials through blending and bedding? And which raw material characteristics create the biggest challenge for maintaining stable sintering performance? Over to you, sir.
Yeah, first of all, in Kalinganagar, we have one of the largest sinter plant in India, that is 496 square meter. And just to share with panelists as well as the audience, this 496 sinter plant has capacity is 5.75. Happy to share that we have produced 6.3 million ton last year with a quality consistency of tumbler index more than 79, RDI less than 20. So we had a very good result in financial year 26, which we are continuing this year. Now, coming back to your query related to the iron ore fines, first question was related to the variability in iron ore fines. Yeah, so first of all, to all the audience and the panel audience, I mean, is that when you are running a sinter plant, where are you placed? Suppose if you are in engineering and project, your way of approach will be different as compared to when you are running an operating plant. Now, in an operation plant, you have been given an equipment which has got certain design features, and the rated capacity. You need to understand that and then optimize the process to get the quality product. Okay, so coming to the sinter plant at Kalinganagar, we have two important units in sinter plant. One is the raw material bedding and blending plant, and then the sinter machine. Now, this, as I've already indicated, a 5.75, we have produced 6.3, and the bedding and bending plant, we have produced 7.9 million ton. Now, variability of iron ore fine, the first fundamental, we have strengthened the testing facilities, because the testing facilities under the scientific services and CRMT lab, we need to understand what are the Fe content, what are the silica content, what are the alumina content in iron ore. Now, already spoken by Dr. Rameshwar that silica and alumina, these are undesirable. So once you know what are the different components of alumina and silica in iron ore, we do have a strategy of blending. Now, when we do blending in RMBB, we do blending the proper way, and then we first is the stacking process, then the blending, and then dispatch to the sinter machine. Now, in sinter plant at Kalinganagar, we have a 496, which I've already indicated. We have 124 meter length. We have taken the advantage of this design. The longer sinter machine has got a process capability to take care of the variability, and we have strengthened the daily management process, where we have optimized water in mixture and nebulizer. We have optimized the waste gas fan, a very strong daily management practices there to take care of the bed permeability. Hence, the variability is absorbed, minimized, some in stacking, some in blending, and then in the sinter making machine itself, and then we get the output.
Thank you so much, Mr. Rakesh. Moving to the next panelist, we have Dr. AVB Acharyulu from JSW Steel R&D department. So my question to you is, as we are aware, granulation is a crucial parameter in the sintering process. What are the recent trends across the globe and in your experience, which have been successful and which hasn't been, and why?
Thank you, ma'am, for the question. So, on the extreme end, China has tried almost 110 kg of calcined lime and dolo put together to maximize the granulation. And in India, we are going somewhere between 20 and 60 kg per ton of sinter. Calcined lime is most commonly used binder. Alternatively, there have been attempts to use lignin, bio-based binders, activated binders, and players like BASF, Bushan, we have a great experience of trying those binders. There are various results coming through alternate binders also. Yeah.
So if you could tell us which have been the successful ones and which were not successful.
No, it's proprietary, so I would not put my comments. But there have been some issues with these alternative binders in the sense that these binders work very well in pellet making because the particle size is small in pellet making. The overall surface area is more. If you look at the input raw materials of the sinter mix, the particle size is large. So to have a coating of this binder, you will require huge amount of material. In the first place, the binder itself is very costly, and to afford such a large quantity of binder in sinter making process looks to be economically not viable. Therefore, the attempts are getting limited. But yes, theoretically speaking, they improve the granulation index a lot.
Okay. Thank you so much, Dr. Acharyulu. So to our panelists, the audience have already started raising questions. You can review in your Q&A box. Meanwhile, we are continuing our next question. We have Mr. Anish with us from MNS.
Good afternoon.
So, Anish ji, my question to you is, at Hazira, how do variation in ore chemistry, especially in Fe, silica alumina, and LOI, influence your sinter blend design? And what parameters are most critical in deciding the optimum blend, Anish?
Yeah, ma'am. As we already heard from Rakesh sir, that alumina is the major concern for the future trends of the sinter plant. So we also have this philosophy to control the alumina as much as we can with higher basicity and MGO models. So using the futuristic the past data, we can try to simulate the future if we can with the growth of the AI and the AI ML models. This is possible with physics and simulation in collaboration. It can be done. It is an answer to what we are searching for as a center specialist. For in concerns of the high raising alumina, also the volatile organic compounds plays a major role that we go through, because we have a zero waste policy over here at AMS India, and we try to use the 95% of internal waste generation that is being generated all over the asset. So the VOC is a main system lacuna that we face, and we are trying as much as we can to sustain so that it will always have a benefit for decarbonization and always gives a benefit to the environment from our end.
Anish, I have another question for you from the sinter plant operating perspective. Since you are there as a technical expert, how do you optimize granulation, moisture, and bed permeability to maintain a stable flame front and achieve the desired productivity and sinter quality?
Right, ma'am. At present, what we are doing is we are having a moisture control roof for the Wayman systems of the internal circulation. Further, we are trying to develop a controlling loop in measurement of the internal materials or the input materials with the output one. So there will be a complete control loop using the AIML programs that is being developed at present. We are studying the feasibility of developing it with the deviations that we generally get throughout the monsoon seasons. So that is the major part when we face the tendency of the deviation of moisture in the fines. So we are trying to control that. It is under study, and we are trying to develop the controlling loop using the AIML programs.
Thank you so much, Anish. Moving back to Mr. Rakesh. So how does the choice and quality of solid fuel, particularly coke breeze and alternative carbonaceous material, affect flame front stability, productivity, and center quality? And where do you see scope to optimize fuel consumption?
Okay, now coming back to the fuel. So if you ask me as a sinter maker, it is always preferable. Coke breeze is the preferable. And again, in any process, when you are going for a high level, the testing facilities should be perfect. So like in coke breeze, we should be very clear what is the ash level, okay, and what is the carbon level. Now in Kalinganagar, we have got that advantage. We have only one single source of coke breeze because we are getting from our coke plant. But the important thing is, again, I repeat, when you are running an operating plant, the daily management should be very strong. The coke crushing fineness should be very good. And the coke crushing fineness, which we are doing at RMBB, it is very well maintained, which helps us in a proper run through and a proper heat input to take care of the variability in iron ore fines. Higher alumina will definitely require more heat input through the coke breeze, which we maintain. So practice is that we have only single fuel, that is coke breeze. We use in RMBB, in pile making, and for trimming, we use coke breeze again in sinter making. I hope I have clarified.
Yes, sir. Yes, sir. And I have another question for you. From the Kalinganagar experience, what aspect of center plant design and equipment selection have the greatest influence on productivity, if you could tell us? Permeability, heat utilization, and consistency of center quality.
Okay, so now again, in my the first question which you had asked, again I repeat, in which department presently you are. Let's say if you are in operation department and you have been given certain equipments, you need to properly study and understand design. However, if you are in the ENP engineering department and you are going to build a sinter plant, you have to be very careful with the technology selection, what you are doing, what are the equipments being done. Second is that, as already indicated in Dr. Rameshwar presentation, the customer is blast furnace. What are the sinter requirements for blast furnace? Whether they are going to operate at 65% burden, whether they are going to operate at 70%, and then whether they are going to operate at 50%. In that basis, you design the sinter plant, taking care also of the environmental aspect. What are the choice for ESPs you are going to select it, so that you are supposed to maintain certain norms. So all depends upon where you are. If you are in the engineering department selection, you require certain do's and don'ts while selecting the equipment. And if you're in an operating department, you have to follow whatever the equipment has been given, understand the equipment, follow the certain principle, ensure that you get productivity, you get availability, you get product quality, and also maintaining the environmental norms.
Thank you so much, sir. So I want to convey to the audience that we have received over 25 messages on the question Q&A box. However, I request all the audience to specifically mention who you want to ask question from, because these are all open-ended questions and I don't know with whom I have to take it up. But I'll start with Akansha Gupta. She has asked, can you describe, due to goethite-based ore sintering, how do you do the fit calculation? Is it calculation FE or total FE, or can you illustrate goethite in terms of process for complex vertical DRI? So I request the panelists to, suggest who want to answer this question. You can volunteer to answer this. Yeah, Dr. Rameshwar. Sure.
Go on, sir.
The question is how to optimize the goethite ore.
Yes.
The goethite ore is a kind of weathered hematite ore. So it has more basically the hydroxides, which basically the water is there in the form of a crystalline, you can say, molecules there. So these are not the surface moisture or which can either go off when you just heat the materials and go. So it remains with the material, and once you make either the sinter process, so once it goes into the sintering, these crystalline, you can say water molecules, they basically gets released at a temperature 250 to 800 degrees Celsius. So what it happens, this is basically a kind of LOI that we call it loss on ignitions. So to handle this goethite ore microstructure, during this process, either it requires more of the heat. So more coke bridge requirement will be there. So that if you know that you can say it is the goethite ore, and if you have the basically the phase analysis, how much the you can say goethite is there into that overall blend of the sinter, then basically we take charge of the you can say the fuel consumptions. Normally the goethite ore that could be there, it requires little more of the solid fuel that basically we base. So that it should not, the process should not get the energy deficient where you can say we could not be able to make the proper melt, the partial fusion of the material, so that it should not obstruct the proper bonding during the sintering process. So the goethite ores, whatever it could be there in terms of the you can say fuel requirement, that we can take care of. If any loss on ignition is there into that process where it may generate some you can say vapor or the moisture, that could be taken care of while it goes through the you can say ECP process. So this blend optimization has to be done, and that is normally done while bedding of this you can say sintering, and you can say the blend optimization. So that could be taken off. But if it is disproportionately very high, then basically we have to go the entirely a different set of calculations for the sintering process.
Thank you. I hope, Akansha, you have got the answer. We are taking up another question from Dr. G.V. Rao from NMDC Limited. His question is, the sinter plant is normally optimized for productivity, fuel rate, and cold strength, whereas the blast furnace needs permeability, reducibility, and good softening melting behavior. How can we establish a closed loop sinter BF optimization system that dynamically selects the least cost raw material blend and operating conditions while minimizing total hot metal cost and CO2 emission? Anyone can volunteer. I see Anish smiling. Anish, you want to answer it?
Basically, you have to define the system apart from optimizing the variables or the process control variables. We have to define the sinter dispatch system for the whole routine, because the number of faults always leads to the multiplication of the deterioration of the sinter. The more number of faults or the kind of dispatch system you have, like for example, we had faced multiple faults issue in Sinter Plant 1 at AMNS India. So we are planning for pipe conveyors for Sinter Plant 2, as the distance between blast furnace and SP2 is greater. So accordingly, apart from the AIML systems, we have to constrain the basics of sintering rather than keeping our eye only on the previous data or the data that has to be analyzed for the better optimization values. So it kinds of concise the things that the physics always overleads the AIML part, and for physics we have to look at the material also, or the basic systems also. So if it answers the questions.
Yeah, thank you so much, Anish. Coming to Mr. Dr. AVB Acharyulu. Sir, what are the decarbonization trends now? And if I want to understand from the JSW perspective, and how is the Indian Sinter fraternity faring? How much coke rate are you able to reduce through incremental decarbonization steps, sir?
Yeah, actually, there are two varieties of decarbonization which are on. One is deep decarbonization, and the one is incremental decarbonization. At JSW, we have a program called SEED, which is basically a brainstorming kind of a program. We gather various ideas that can reduce the fuel consumption and implement one by one, see its effect, and cherish the achievements. So starting from moisture optimization, starting from you have calcined lime and other binders, optimizing them, maximizing the usage of calcined lime, and preheating the mix, injecting steam into the various locations, which is mixing and nodelizing drum, or be it raw mix bin. So you preheat the raw mix and then reduce the amount of fuel required for sintering. And we have fuel gas injection trials going on. We have already established coke oven gas injection system on sintering bed. Various biofuels, biochar, mass is being used to replace the coke consumption. For more than 15 years or so, we have been using anthracite as an alternative fuel, which has got less footprint than the normal coke fines, because coke has to undergo carbonization process, which requires a lot of energy. So if you compare anthracite with coke fines, anthracite has got edge over the coke fines. Talking about decarbonization, I mean, the technologies are yet to evolve. You see, so could be, I would say, the OEMs have to, put a lot of efforts to achieve those decarbonization targets. But I can say 10 kg per ton of solid fuel saving is achievable as of today with all the efforts on. Regarding this energy efficiency, we can have.
You're saying in Sintering 10 kg of fuel saving?
Yes, yes.
Okay.
Suppose if I am at 60 kg per ton of Sinter, the solid fuel consumption, yes, we can target 50 and try to achieve. I mean, this is the kind of stretch target, but yeah, we can optimize a variety of techniques by which the carbon rate can be brought down. Yeah, and regarding this energy consumption reduction, we have waste heat boilers, power generation. The technology has not so advanced. You have to capture the heat wherever it is lost. Suppose I have an installation on wind boxes, wind main across the ESP and wind main system. My energy efficiency will be more, and capturing, it's a common jargon that wherever energy is getting wasted across the steel plant, it is not viable to capture that waste heat to convert into various power or steam, such kind of applications. Yeah.
So, Dr. Acharyulu, there is a concern shared by Christian Moria. The parameters which are optimized the Sinter RDI, we are getting FEO in the range of 9.5% to 10.5%, but still RDI we got is less than 27. So, if you like to comment on that.
Yeah, optimizing within the Sinter plant, whatever is available, playing with the waste gas fan speed, maximizing the bed height. I mean, this figure could be in the range of 22, I believe so. If an audit has to be conducted and look into those details, it is possible, I think.
Okay. There is a general question from Mr. Glenn from Goa. He's asking, when we talk about the low-grade iron ores, what would be the preferred iron ore content, silica and alumina content for input for sintering plants? Can a typical ore having a Fe content 50 to 53%, alumina 4%, silica 4 to 6%, moisture content about 10% be suitable? Or there will be another needed concept for beneficiation needed prior to improve the input feed to Sinter plants? Rameshwar, Dr. Rameshwar, yeah.
If it is the low grade ore, if I try to reframe the questions, then if it is the low grade ore and
Yes.
they say it is the Fe level is 52, 53, the
Yes.
silica and alumina will be much higher. What the figure that you have put it, the first thing. If the alumina particularly, I'm first coming to the alumina, if it goes beyond 3.5%, and that either this ore goes to Sinter or maybe even with pellets, it is not good because it has a very detrimental effect over the process. So if alumina is more than 4%, 5, 6%, whatever, it has to undergo through the beneficiation process. So far the siliceous ores are concerned, where the silica is high, silica can be, it is also detrimental, but it having the less impact than the alumina. But silica to the level of even 5 to 6, 7% is I think acceptable, because this sometimes by maintaining the basicity helps in making the slag bond formations. So if little higher silica could be acceptable, but more of this alumina will not be acceptable. This low grade ore has to undergo the beneficiation and upgrade to the level where this preferably the alumina could be brought less than 3%, and silica could be 5 to 6% range.
Okay. So, we have received over 40 questions. We may not be able to take up so many, but we will try to take as many as questions we can. Coming to you, Rakesh ji, we want to understand that sintering is one of the key emission intensive process in an integrated steel plant, which environmental control systems and waste heat recovery solutions are most critical for controlling emission while improving energy efficiency in sintering.
So if again the plant which we are operating, we don't have the waste cooler heat recovery, so I will not comment on the cooler. Again, I repeat, we are in an operating department where we have been given certain technology, we are using that. So if you ask me for a plant which is running with electrostatic precipitator, first of all, be very clear. Whenever you're running an electrostatic precipitator, there will be number of fields. Let's say 5 fields, 2-pass design. Ensure the fields are available. That is important. That is the secondary voltage milliamps are available. Then only you will have a good emission results. How to make it available? Couple of points. First point is that you need to have a proper operation maintenance strategy. The operation strategy is that you need to operate the plant at a particular ESP inlet temperature. Normally in sinter making, it is advisable to operate between 130 to 160 degrees centigrade. More than 160 is not good, less than 130 is not good. Second operating discipline is the CO content in the waste gas analysis. You are supposed to maintain less than 1. Higher the CO percentage, that is also not good for emission. So these are a couple of things on the operating discipline. On the maintenance discipline, please have a proper maintenance strategy during the shutdowns. You must have a proper internal inspection of ESP. And if an ESP are of different design, so obviously I'm talking about, let's say I'm talking about a tumbling hammer design. You must have a proper maintenance strategy of going inside ESP during shutdown, inspect the fields properly, and then see that the wrapping mechanisms are working properly. These two strategies, if you are maintaining, you will be able to maintain emission less than the norms which has been established when you are selecting the equipment. So when you have selected equipment where the emission level is supposed to work less than 50, you should operate the plant to get that results. That is my answer.
Thank you so much. Coming to you, Anish, when there is a sudden deterioration in center quality or productivity at Hazira, what process parameters do you typically investigate first? Is it the bed permeability, suction, strands, speed, fuel rate, return fines, or something else?
Whenever the process go wrong, it is easily visible on the loading set also. So just before the furnace, we have the suction tips. It can be exactly stated at that point. Going on, the trend of the burn through point and the suction parameters will definitely be a resultant of your faulty processes. So, and the final resultant will be the increased consumption of return fines. So while we adapt to look at the process, the initial suction parameters, we also have a philosophy to check out the changes in materials that we feed in. So any chemical changes or physical parameter changes, the size of the material that we have to coach on and look onto it. And simultaneously, the return consumption and the coke variation in fixed carbon of the coke. That are the main parameters we have to look at.
Thank you. One more question I want to ask you, Anish. How do you manage the trade-off between the higher center productivity and key quality indices such as tumbler, strength, RDI, and reducibility, but particularly considering their downstream impact on the blast furnace?
Okay, ma'am. So our philosophy is not to maximize the productivity only. So we optimize the quality and cost for the iron making zone. So basically, we have to carefully balance the fuel rate, the basicity, using the bed height and strand speed for the productivity. Our targets are lower than JSW and Tata Steel for tumbler index and RDI because of the feed we taken and the philosophy we have at the consumption of the material at blast furnace, that is around 35 to 40% of the sinter is being consumed in blast furnace. So our philosophy is developed on that, so that no input of flux is there at blast furnaces. And for RDI, basically we have to chalk down on the RDI because using 95% waste material as a detrimental effect on RDI. So we have inbuilt an RDI prediction model for ours. So at basic process parameters, we have tried to develop an RDI prediction model using the past data and some calculations. So at particular getting the minimum process parameters, we can predict the RDI for the upcoming material or product.
Thank you. So I will take 2-3 more questions and then we will have to conclude the webinar because I believe the questions will not end. We have a question from Tamilarasan. He's asking, can we use microfines up to 60% in raw mix? If we have a rich mixture, is it proven to any plant? What is the maximum microfine percent in raw mix we can use in sintering? Who would like to answer this? Can volunteer. Yeah, Dr. Acharyulu.
So yeah, 60% microfines is not a surprise to us. And we have 2 sinter machines where we have twin Irish mixer and nodalizer, as well as a combination of 2 mixing and nodalizing drum. So with 60% microfines, also with increased calcine lime, we could survive. That is number 1. When I talk about the high intensity mixer and granulator, if the pan is tilted, the performance of these machines will be ensured. If you have a flat pan, then there are challenges if the microfines goes beyond 30%. Yeah.
So I'm taking another question from Pradeep Sharma. He is asking, what is the range of base mix Fe% to maintain the Sinter FET 55%? Who would like to answer that?
A lot of mathematical calculations and data analysis will be required to answer this question. So,
okay. So are we passing off this question?
yes.
Okay. Isn't there so many? I'm just thinking which one to pick it up. Okay, we are taking a question from Rushi Raj Raval. His question is, what is the maximum proportion of anthracite coal that can be used while maintaining an optimized sinter process? Yeah.
So in 2011, we introduced anthracite and we went up to 100% during trial phase. So we did not find any much adverse impact. We went up to as high as 75%. Koreans caution.
Yeah. Please continue.
75% in the solid fuel blend.
Okay.
If you look at the Korean literature, it says if you are continuously using anthracite at higher level, the crushing index has to be much better. I mean, they target 1 millimeter size as an optimum size for anthracite.
Yeah, thank you. Dr. Ramesh, you want to add or?
I want to add.
Oh, okay, Rakesh.
So while using anthracite, again, I repeat, first, be very careful with the testing. VM matters a lot. Anything over 5%, you will be in trouble in ESP. So be careful when you are using anthracite. It should be less than 5%. I repeat in my question and answer when Monica asked me, preferred fuel is coke breeze. However, there are possibilities in any steel plant where coke breeze ability will not be there. You have to use anthracite. But if the VM is less than 5, you will not have problem. But if it is more than 5, you will have problem during the sinter machine outages. There will be challenges where you will have to problems may come in ESP.
We have a question from Shiv Shankara. So what is the opinion on plastic noodle using as fuel in sintering process to reduce the CO2? Plastic noodles. Anyone can volunteer on that.
I think so far no industry since sinter plant in practice have used, but this plastic noodles has been in use as a supplement to the fuels. This either in electric arc furnaces or may have used in the coke ovens, but in sinter plant so far are not being practiced. But anyway, to certain proportion, because these are all the volatiles, it is mostly the gases. If you look at in the plastic noodles, the carbon residue could be 15 to 20%. rest all are the gases. So increase, maybe the use of this may create problem for the ESP or that part. So for the, I think I just like to add for 10 seconds what Brahmacharya Sahab and Rakesh Sahab. We had optimized this, you can say, anthracite coal to the level of 50-50%, provided that he rightly said that the VM should be less than 5%. So where normally the 4% of the VM, and if your coke bridge, if not availability, then we can definitely go for that. Otherwise, it is not advisable to go for 100%. The another reason is that this has a very poor combustibility of the anthracite coal than that of the coke bridge elements.
Okay. I'm taking up one last question. This is from Shweta NLMK. Shweta from NLMK. Her question is, does the Syncat product has the catalyst for fuel combustion regarding coke fines? ये तो आप ही को आंसर करना होगा. Abhitech has to
Bhushan, you may answer.
Actually, yeah, this is basic. Yes, Syncat also has a catalyst which improves the coke breeze combustion, and therefore the coke breeze consumption should also go down. However, we are looking at coke breeze itself as a decarbonization initiative to reduce coke breeze consumption in the central process, to look at it as a decarbonization initiative separately. So while Syncat will do that, it is yet to be established, and we would prefer to give a separate solution for that, which would be more cost effective and which would be more powerful. Yeah.
So with this, we have to conclude the webinar. I would request Bushan ji and Dr. Rameshwar to say some concluding lines, and then we will conclude this webinar for today.
Let me first intervene, then Bushan sir will probably give it a final song. So far, this the topic of the webinar that we have selected, it's very apt, very relevant, and very useful. And though the sintering as a process is well established, more than 100 years old process, has got several leads of life, and as Ambastha told very rightly, that you need to basically understand the technology. We have to understand the equipments and the working there. So keeping those parts, because you do not have the liberty, or you can say that pleasure to have always the best quality of the raw materials, the best operating processes, or you can say best operating conditions, are everything there. So given the circumstances and the conditions where we need to basically have, you can say, all these constraints to take care of, as this online monetary system, predictive models and others, which I think at length Mr. Anish Mohapatra has explained. This basically always helps sinter makers to control their processes, to know in advance how their process is going to behave, what kind of product they are going to finally produce. So all these digitalization, all these lot of data analytics are required, and all these inclusively, these things will definitely help to produce a better sinter quality, better productivity, you can say higher productivity, and the right kind of product for that. And definitely anything that is as external additive agents that could be there, because additive manufacturers have become a very big field altogether all over the world. Like there are the different courses in master, the people go for additive engineering also. So those things are growing up, and it will definitely going to, you can say, contribute a lot in further, you can say, solidifying these processes, or making this sintering a more, you can say, the robust and a stronger process for making the product, which can be right kind of the product useful for the blast furnaces and steel makers.
Thank you, Dr. Rameshwar. Bushan ji.
Yeah, thank you so much once again. Well, with the advent of now with more increasing emphasis on CO2 reduction and decarbonization, CO2 reduction, CBAM mechanism already being implemented in India, or being enforced by the government in many of the countries, and many countries already following it, it is of importance that sintering, it's no doubt that sintering will play a very crucial role in overall decarbonization efforts of the steel plant, and to reduce their carbon intensity. Many of them are operating beyond 2 kg or 2 ton per ton of steel, and that is very, very significant, and they need to reduce it, and sintering can play a very crucial role. and any impact on the quality of the sinter and improvement in the quality will make a significant impact in the blast furnace productivity and thereby reduce the overall CO2 emission intensity. So thank you very much once again for the active participation of all the participants. Yeah.
Thank you so much to our esteemed panelists and to our audience. This was indeed a wonderful program which was sponsored by Abhitech to us. Viewers, you can also propose your subjects if you want to have some technical or policy related discussions to our programs. You know, Metallurgic has a reach of over 25,000 steel professionals in this field, and I hope we will be able to get you better solutions going on. So thank you so much for your time, and everyone, let us have a great evening, have a tea and coffee, and let's break this session here.
Thanks
Thank you
to
so
you
much.
for also nicely conducting all our speakers, esteemed guests, and the audience
Thank
for
you.
the presence, hearing, and
Thank you for the
participating.
panelists. Thank
Thank
you
you,
for
sir.
taking your time and joining for the webinar, sir. Thank you personally. Thank you very much.
Thank you, Rakesh
Thank you.
ji, Anish ji, and Dr.
Thank you, sir.
Acharyulu, Dr.
And the
Ramesh, and Mr. Bhushan. Thank you so much.
Thank you.
Yeah.
Thank you, sir. We'll meet again and we'll be in touch.